Hello and welcome to my individual research project output design video, enhancing methods of transport through use of modern batteries and motors within an electromechanical powered system. For my output design, I'll be taking you through the design, manufacture and development of an electric longboard. Aligned to my research project, the electric board will utilise modern battery, electronic speed controller and brushless motor technology to minimise the dependence upon combustion engine vehicles for inner city and town commuting to reduce the carbon footprint. To design the deck, I used the CAD package SolidWorks to design a unidirectional shaped deck to travel in both directions. The deck is 1 metre long to aid stability at speed, features a 10 to 12 degree concave for flex and shock absorption over terrain and bumps, and made up from 3.6mm laminated lightweight sheets of maple ply. The low centre of gravity would help to ensure easy and precise control at speed. To manufacture the deck, I laminated 3 lots of 3.6mm lightweight maple ply sheets together using all-weather wood glue, ensuring the sheet's natural grain flow was opposing between ply layers to avoid stress points from the natural grain flow. The sheets were clamped together using vices and a heavy brick positioned in the centre of the deck to produce the concave bend within the deck profile. The laminated sheets were then left to set and cure for 24 hours. Once set, the sheets had successfully laminated together with a perfect 10 to 12 degree bend across the length of the maple ply. A quick load test confirmed the sheets felt flexible for forgiving feedback but with good stiffness. From the CAD model, a template was produced onto a thin sheet of ply to transfer the design onto the laminated sheets as a stencil. Using a fine-tooth jigsaw, the template shape was cut from the laminated ply. The sheets of ply were then tested under load once cut to size, confirming good flex and rigidity. To further enhance the deck's rebound and flex, I opted to manually apply layers of carbon fibre to the deck to enhance the deck's rebound, flex and aesthetics using raw carbon fibre 2K twill. Carbon fibre is a modern material consisting of thin, strong, crystalline filaments of carbon used as a strengthening material infused within resin. To laminate the maple deck, resin was carefully mixed with hardener and applied. Once tacky, the first layer of carbon fibre is laid upon the resin to tack and left for 10 hours. A second coat of clear resin is then applied and left to cure before sanding and trimming the edges flush with the deck. The resin is then sanded back using coarse grades of grit paper to remove any imperfections from the resin to leave a smooth surface. The surface is then cleaned. A third coat of resin is mixed and applied before sanding back to a fine finish, working from 400 to 2,500 grit wet and dry paper. The carbon fibre was then given a finishing cut and polish using fine abrasive polishing compound to leave a flawless finish. The process was then repeated on the underside of the deck. Again, using SolidWorks, I carefully designed a number of battery and electronic speed controller housing designs. As the project was a one-off, I elected to use additive manufacturing to produce the housings. Limitations of AM, such as draft angles and print resolution, were carefully considered throughout each design iteration. For the final prototype design concept, I opted to house the battery and speed controller together to keep the design as flush and compact as possible. The design was adapted and shaped to follow the contours of the large high voltage battery pack and slim streamlined design of the speed controller PCB, featuring a number of undercuts. Due to the design, 3D printed support structure had to be carefully integrated into the print design to support the print. 6 M5 bolt holes would ensure sufficient fixing strength to support the weight of the heavy battery. The first prototype was printed on a Mark forged AM printer that utilises carbon fibre infused within the resin of the print media for added strength. The first printed design successfully housed the battery and ESC components, but bench testing identified that excessive heat was dissipated from the speed controller as it regulated the speed of the two 1000 watt Hall effect brushless motors. To prevent overheating, the design was optimised, featuring honeycomb-shaped vents that extrude from the design and an aluminium heat exchanger plate fitted to the ESC to allow for air cooling. On-off switch port and a charging port were also integrated into the housing with appropriate print support structures included. However, unfortunately, the additional cooling vents were in the same print region as the printed support structure. I did not evaluate the printed support structure design effectively, which resulted in 2 failed prints after the design collapsed due to the addition of the cooling vents. I carefully re-evaluated the AM support structure design, print layer and wall thickness settings to optimise the print to further prevent collapses. Once successfully printed, the support structure was removed and the housing mocked up on the deck for positioning. From the CAD model, a stencil template was printed to mark the position of the threaded wood inserts to secure the housing to the deck. A pillar drill was used to drill the precise depth of 12mm to prevent the drill protruding through the deck. A mock fit of the battery and ESC was performed, but under vibration identified movement of the battery and ESC within the housing. A thin foam gasket and padding was used to cushion and protect the components under vibration to carefully retain the parts. The brushless hub wheel motors and trucks were mounted to the deck before the programming of the receiver and ESC was required. The project was really beginning to take shape with a stunning and professional finish. The motors selected consisted of two 9056 60 kV 1000 watt Hall effect hub motors. As the rotor's permanent magnets rotate, the Hall effect sensors senses the magnetic field and generate a logic high for one magnetic pole or logic low for the opposite pole. From this information, the electronic speed controller can be programmed when to activate the next rotor sequence or interval. The precise timing of the electronic speed controller allows for accurate speed and torque control, as well as ensuring the motors run at peak efficiency. This precise timing from the electronic speed controller is managed via the VESC ESC programming software that allows for precise timing and phase angles to be achieved within the motor to achieve peak efficiency and performance. The maximum current and voltage figures are defined within the software to limit the power demand from the battery and motors, ensuring they function within their peak operating range and to prevent damage. Within the VESC programming tool, regenerative braking can be programmed, allowing the motors to charge the battery under braking. Regenerative braking allows the hub motor to act as a generator to convert much of the kinetic energy lost when decelerating back into stored energy within the battery. Regenerative braking typically enhances most electric vehicles' efficiency by up to 15%, helping to further reduce emissions and increase range. Next, the throttle receiver was then programmed using the VESC tool. Steady and proportional position versus output curves were loaded onto the receiver to allow for smooth and steady acceleration of the electric motors to ensure stability. The battery was charged and the system tested. Here you can see the honeycomb cooling vents and the aluminium heatsink plate to cool the ESC when running. Preliminary test results were highly successful. The board felt stable with progressive and powerful speed and acceleration. The smooth carbon fibre finish, however, had compromised the grip between my shoes and the deck, resulting in a few near-miss accidents under heavy braking and acceleration. I opted to apply grip tape, which is a self-adhesive tape formed from coarse grit to form a rough surface finish to increase the grip to the deck. This would help to enhance the grip of the deck under normal or wet riding conditions, helping to enhance the confidence further of the end user. But when applying the grip tape, I did not want to compromise the carbon fibre aesthetics of the deck, so carefully designed a uniform honeycomb grip tape pattern to be cut with a high power laser cutter. The cutouts were then applied to the surface of the deck, offering significantly more grip. Initial performance testing using a GPS measured a top speed of 28 miles an hour, sufficient enough to navigate the streets of most cities and towns bound by a 30-mile-an-hour speed limit. The power of the motors was sufficient enough to accelerate and brake on 10 to 15 degree incline slopes with my 90 kilogram load, offering good performance in most town and city suburbs. I then performed 2 range tests to measure the maximum distance the board could travel before the automatic voltage shutoff feature was activated. I previously programmed this within the battery management system using the VESC software tool. I performed the test along a 3-mile cycle path which featured a number of inclines and decline gradients as well as sharps, twists and turns to navigate to replicate a typical suburban environment. The first test was performed with repeated heavy acceleration up to its top speed and sharp deceleration, achieving a range of 8 miles. The second test was repeated along the same test track but travelling at a slower, smoother, steady speed of 10 to 15 miles an hour. From the second test, I recorded a range of 12 miles. The range had increased by 50% with a steady and smooth riding style, highlighting the inefficiencies associated with accelerating a mass up to speed repeatedly. I was very pleased with the overall project end result. I've learnt and developed additional skills in CAD and additive manufacture, which before this project I had extremely limited exposure to. My attempts to size the system, selecting appropriate brushless motor types, batteries and speed controller components was successful thanks to careful calculation and budgeting of the project components. The torque output from the motor is currently limited by the maximum discharge rate of the 10S 2P lithium cell battery. On occasions when riding uphill, the board does feel like it could benefit from some additional torque. The most effective way to increase this torque within the system would have been to select a higher discharge capacity battery, such as a 12S 3P battery cell, offering up to 20% more torque. However, this high-spec battery type was typically considerably more expensive, bulky and heavy, which would have exceeded the £500 project budget and compromised the slimline battery housing design. My total output design project spend came in just under budget at £475, involving approximately 100 hours of designing, manufacturing, assembly and testing.